In this video, we're going to look at esters. Now, esters are a very interesting molecule, and you've run into esters lots of times and you won't even been aware that you ran into them. So, esters are commonly found in nature. They're produced by plants frequently, mammals, all sorts of organisms create esters. But notably, esters are responsible for some very pleasant smells and flavors. So, vanilla and strawberry are ester molecules. And in nature, the esters are going to be a combination of many different, there'll be many esters that contribute to the flavor. But there's sort of a core flavor that is related to one of the esters. And so you end up getting things like fake vanilla that you could buy in the store, is cheap to buy. And it's going to be one ester that is like vanillin. It's a flavored ester. Now, if you get vanilla from nature, it's extracted from vanilla plants, that's an orchid, and it's a complex combination of many different molecules. And so it tastes like there are more flavors to it and it's more complex. Same with strawberry. If you went and bought like strawberry quick, it's going to taste fake and it's going to taste, you'd be like, oh, that's strawberry, but that's not real strawberries. Because real strawberries are a collection of many molecules. But there is one kind of notable strawberry flavored ester, and it is going to be the kind of molecule that we're going to look at in this topic. So esters have an ester linkage. The ester linkage has got a carbon that has got a double bond to an oxygen, so that's a carbonyl, and it also has a single bond to an oxygen. So that looks a lot like when we studied carboxylic acids, but now instead of this being a hydrogen, it's going to be an oxygen will bond to another carbon and a chain potentially attached to that. And so once this is like this, it becomes much less polar a molecule because it doesn't have hydrogen bonding. It does not have a hydroxyl. So esters have a lower solubility in water than alcohols or carboxylic acids, and they have a very distinct odor. Now we can produce esters in a lab by reacting an alcohol and a carboxylic acid. And these kinds of reactions are often referred to as a condensation type of reaction. So a condensation reaction produces water. So when we did an elimination reaction with alcohols, it also gave off water and made double bonds. That's a condensation type of reaction. In this case, though, what we're going to have is the hydrogen from the alcohol and the hydroxyl from the carboxylic acid form the water that condenses out. And then what we get is the oxygen here bonds to the carbon here and forms the ester linkage. So we end up getting this ester linkage in here, and it's from that hydroxyl from the alcohol reacting with the carboxylic acid end. The naming of esters is actually fairly straightforward. It's going to be a branch name and the parent chain O8. So this is methyl ethanoate. But the way that you decide what the branch is the branch is the part that came from the alcohol. So methanol makes methyl. And then the parent chain, the O8, comes from the carboxylic acid. So this is ethanoic acid, it's an ethanoate. So methanol and ethanoic acid make methyl ethanoate and water. Now, this particular way of writing it, where you write alcohol and then carboxylic acid, that's the way that I like to do it if I'm asked to draw an esterification reaction, because it makes the naming extremely straightforward. Alcohol and then carboxylic acid are how we come up with the name. But it doesn't have to be drawn that way. They could give you the carboxylic acid first and then the alcohol. So in this case, they've got ethanol reacting with propanoic acid. So this makes ethyl propanoate and the water that comes out from it. And so it's a common kind of question might be to ask what the products of the reaction are, or if here's the name of the carboxylic acid, what are the reactants that would produce that carboxylic acid? And if you know that the alcohol is the branch name and then the parent chain comes from the carboxylic acid, it's pretty easy to figure out. Now, this particular ester here, we're going to name. This part comes from the alcohol, and this part is from the carboxylic acid. So since this is going to be from an ethanol, it's ethyl, and this is 1, 2, 3, 4. This is butanoate. So as long as you can spot where the alcohol is, it's pretty straightforward. Let's condense this formula down though and see how it can get a little bit trickier if you're trying to name it with condensed structures. This would have been a CH3 from here, CH2, CH2, COO, CH2, CH3. Now, when I look at this, this looks more complex. I can't easily spot which spot or where the alcohol is and where the carboxylic acid was in here. But if we take a look and think about what we're looking at, we can sort it out. This carbon has got no hydrogens attached to it. It is attached to this carbon, so that's one bond. So these must be from the carboxylic acid. So this is going to be a 1, 2, 3, 4. That's a butanoic acid contributed to it. This carbon has two hydrogens and is bonded to this carbon. So it's only bonded to one of the oxygens. That's from the alcohol. So that's ethyl butanoate. If I turn it around, so I'm going to turn the molecule around. I'm starting from this end, CH3, CH2, OOC, CH2, CH2, CH3, you can see now that this carbon is single bonded to this oxygen, so that's from the alcohol, and this must be the carboxylic acid because it doesn't have any hydrogens. So I've got an ethyl butanoate. And those are harder ones to spot what's going on, but still quite reasonable in a question to ask you. We've got some different molecules of fruit, and here we're asking you for pear, orange, pineapple, and apple. I'm going to let you try to name those, but before you do, I'm going to just zoom in on orange because this is hard to see. This is a H3C, C double bond O, O, CH2, and then CH2, 6, CH3. Okay, I'm going to let you pause the video and then I'm going to go through these. Okay, so let's pick up with this one. We can see here that this is from the alcohol. This has got two hydrogens and is bonded to another thing, so it's single bonded to the oxygen. So this is 1, 6 is 7, 8. So that's octyl, because it's 1, 6, and another 1, so that's 8 carbons. And then I've got 2 from my carboxylic acid, so this is going to be ethanoate. And if I was going to make this, I'd take oct-an-1-ol and react it with ethanoic acid. Here, looking at the pear, I've got, this is the alcohol part, and so I've got 1, 2, 3, so that's going to be propyl, and it would have been propan-1-ol. And then this is an ethanoate. It came from an ethanoic acid. So if I reacted propan-1-ol and ethanoic acid, I would make that. Here I've got ethyl, and 1, 2, 3, 4, that's my butanoate. And here I've got 1, so that's methyl. 1, 2, 3, 4. So that's butanoate. So These two molecules, I will just point out, I believe they're isomers of each other, right? Because they're both esters, and propyl means three, and ethane means two, so that's C5, and this is a methyl and butanoate, so that's 1 plus 4, and they've got the same number of oxygens as well. So those are going to be isomers of one another. They've got different names and different structure.